So in the remaining part of the course, I'm going to talk about various hardware implementations of quantum information processing. And first in the list is NMR, nuclear magnetic resonance, and how it has been used for implementing and demonstrating various tasks involved in quantum information processing. This was actually the first technique which provided the proof of principle of many ideas, and so historically it is important. The other fact is that it was also implemented at IISc in the lab of Professor Anil Kumar, starting with late 1990s for about 10 years. And many of the things which were demonstrated were actually the first time anywhere in the world. So lots of ideas were implemented, but after about 2010 or so, Anil Kumar retired, and the institute did not invest anything more in that particular direction, so that whole thing kind of stopped. But the method is important to understand from many point of view, and it illustrates various ideas which one has to look for in any quantum information processing platform. So I will first go through the hardware characteristics, and then once we have a full description of the states and the evolution techniques, then we can see how algorithms can be implemented on it. So we start at the very basics. What are the elementary components, the so-called qubits, or they can be generalized to qudits, d-dimensional quantum states. So these are nuclear spins. And how do you construct various labels out of these spins? You want to label 0 and 1. How do you do that? And that is done with Zeeman splitting, in strong magnetic field. So nuclei have spins, but they also have charge. So they have magnetic moments, and you put them in a strong magnetic field, the labels split, and the leading order, which is all that will matter, the splitting is proportional to the z component of the spin, and it is uniform. Okay. So that is as much as we need to know. If you just have a qubit, there are only two levels, and one will be higher in energy compared to the other one. There is nothing more complicated than that. How is this useful? is that we will put together this nuclear spin in what can be called quantum processors, and they are just molecules. But they are diamagnetic. So diamagnetic describes the role of the electrons in the various atoms. You have diamagnetic and paramagnetic and ferromagnetic materials. Ferromagnetics are one which will have fixed magnetization even in the absence of a field. You can put them in that particular state. Paramagnetics are one which can be polarized, where if you put an external field, it will induce a magnetic moment. And diamagnetic ones are the ones where there is no magnetic moment left. And that arises because all the electron spins are paired up. The magnetic moment of the electrons is 0. That is useful to take to a state where the only magnetic moment which comes is from the nuclear spins, nothing from the electron. But the electrons do play a very important role, and that is they give a finite size to the atoms. So in some sense, they shield the nuclei from the external environment. And that is important. So because when the molecules collide, the collision is basically just taken care of by the electrons, nothing much happens to the nucleus. And this is the natural property of these diamagnetic molecules, which gives a particular type of stability to the nuclear spins, even when all kind of collisions are going on between various molecules. So what we can say about this is how many qubits are there in the processor? Well, as many nuclear spins as you can put in. So each molecule is essentially what you can call a quantum register. There's so many number of nuclear spins sitting inside it in some arrangement, and that basically will be used for coding the information and then processing according to some particular rules. So this is a system which is going to encode whatever you want to do. There is a important property of atoms or molecules or any of these fundamental quantum particles, that their behavior is universal, which means if you take a particular atom, say a hydrogen, if you put it in some specific environment, it doesn't matter whether it is the environment in my lab or somebody else's lab, it will behave the same way. And this is a very useful property in terms of making standards and benchmarking and things like that. At the other extremes, that is how astronomers detect some spectral lines, saying that this is a hydrogen and there is oxygen and this is nitrogen. It may be far away in some particular galaxies, but you can tell. And you can tell because it has the same property no matter where it is. This is different than our conventional technology, like there are these chairs. Chairs might be similar, but they are not exactly the same. And if you design this silicon lithography, you make transistors. The transistors are similar in terms of their behavior, but not identical. Here, the systems have the unique property that they are identical. And that is a very useful feature that and this feature will be there in certain kind of quantum information processing, but it will not be there in some other kind of processing. For example, it is there in NMR or it is there in ion traps, where the fundamental degrees of freedom are completely specified, but it is not present in the superconducting technology based on transmons and things like that. And when it is not there, you have to worry about the variations and try to control them. So yes, this is the description, and now let me give them scales. Based on this property, you can actually measure them, that how stable are these objects. Okay. And they are characterized in terms of the decay rates, but the decay rates are different for so-called diagonal parts of the density matrix and off-diagonal parts of the density matrix. It is well known, even based on generic behavior of the density matrix, is that the diagonal part which changes the populations and the off-diagonal part which changes the phases of the density matrix, they have quite different behavior when they interact with environment. So there is a time scale which is called T1, and this is of the order of 10 to 1000 seconds for diagonal elements. And diagonal elements in the generic representation will describe the populations in various Zeeman levels. So it will characterize, for example, the decay time for an excited state to the ground state. It will be in this particular range. And the second time scale is called T2, which is shorter, and it describes off-diagonal elements of the density metric, in particular how fast the phase is of the amplitudes decay. Generally, it is a factor of 10 or so shorter in it is NMR experiments, but these time scales are quite comfortable in terms of handling things in real life. You can respond. Basically, it's large enough that you don't have to automate everything at a very high clock speed. Okay. There is also a generic inequality, which is the property of the density matrix. So the fact that the density metric has to remain positive at the all time, it requires that this T2 is less than or equal to 2 times T1. Showing it for a single qubit is very easy. It just means that the determinant of the density metric should be positive. The sum of the eigenvalues is also always equal to 1, and the determinant will show that both the eigenvalues will be positive. And when you do the calculation for a 2 by 2 matrix, the determinant is just the product of the diagonal part minus the product of the off diagonal part, and the off diagonal terms are Hermitian conjugates of each other, so it gets squared, and the diagonal part appears only 1 for the decaying element, and that is where this ratio comes in, that if the elements are behaving like exponential of minus time. This is how the decay times are defined in any generic processes. You will end up with this kind of relation. So that's a simple fact, but the important point is these numbers are reasonably large. And then one can ask, if I want to perform certain operations, how much time does it take? Because it has to be compared with how long the system will live, and I will come to the what operations we can perform, but I will just give the time scale for comparison. So those numbers are between a millisecond to a microsecond. So there is plenty of range available that within this stable time scale you can do many operations. This is important in any setting that the system has to survive long enough for you to be able to perform various operations.
So, when we talk about decay time, that corresponds to excited state to ground state decay time.
Yeah.
So, for off diagonal element, how we can interpret that phases? Is there any ground state for phase also?
It is the time scale for a process which is called decoherence.
It means it can go to any phase, any random phase after that time.
Yeah, so the off diagonal element have complex values, they have phases, and what it represents is how quickly those phases die, okay, or they randomize or whatever you want to call it. And that if you call this thing a decay, then this is the process is decoherence. And both can be observed independently because all elements of density matrix you can experimentally detect by performing a certain kind of measurements. If you have a qubit, you measure sigma z, you measure the diagonal part. You measure sigma x, you measure the off diagonal part.
After measurement, density matrix would change.
It will change, but you get the result of the measurement. So everything is measurable. These are the numbers which you can experimentally specify by direct experiment without worrying about what model and what other descriptions there may be.
Decay, so does it represent correlations with when you say decoherence, the correlations, random correlations generate system?
These are the processes which occur because of interaction of the system with its environment. We don't know what the environmental details are. That is not observed, and you can forget giving any model for it, etc. But you can measure the system itself directly, and you can see these particular effects. That all the states are going to decay from the excited to the ground state, and if they have off diagonal phases, they are going to randomize and reduce in amplitude. Remember, this is a density matrix, so it always gives a probabilistic description. It is not going to give you a description of an individual event. And where does the probability come? Because you are averaging over all the possibilities of the environment. It's a reduced state. After averaging over environment, whatever remains, it's not a individual state description, but it's a ensemble level description of what happens for the partial trace and reduced density matrix, and what are the corresponding probabilities for observing various kind of processes. Okay. So now I can ask, how are you going to perform various operations? Okay. And for that, the conventional framework which we have discussed many times, you have to figure out how to do 1 qubit operations and how to do 2 qubit operations. And if you can do that, then you can cover the whole space by putting them together in many different manners. Okay. So single qubit rotations. you took the nuclei or the molecule, put it in a magnetic field, and it will give the Zeeman splitting. But that is all the diagonal description, and nothing more than that will happen. If you want to now generate the transformation which for a qubit will correspond to moving around on the Bloch sphere, you need one more operator, Pauli operator. Just the sigma z which comes with it is not enough. So you need to introduce another field which is in the x direction or a y direction, whatever it is. And this is done by applying a radio frequency field. It is a time varying. That is where the frequency came. It's a AC field. This stuff was a DC field. They are in the background all the time, doesn't change. In transverse, which is XY. And so initially the spin may be in Z direction. You apply a field in X direction, so it will rotate about that axis by some angle, and you can go to all the places on the Bloch sphere by choosing a particular direction in XY field. And this direction is completely variable. You can choose in this particular field. So there is a certain convention. I'm not specifying it, but this is a generic description that the frequencies are going to be very different. I'm going to give some more numbers to specify various quantities, but this generates all the rotations and it brings a corresponding number with it. And that number actually is used to characterize all these NMR machines. Okay, they're all given by label for certain frequency. How good is this NMR apparatus? Well, it will tell you this is the number, some 800 megahertz. What does that 800 megahertz actually correspond to? Well, it is this transition frequency of this RF field. Okay, so let me be more explicit. So transition frequency for a proton, which is nothing but the hydrogen ion. It has a number, so universal number corresponding whatever its magnetic moment is, and that specifies the NMR machine something which will be just quoted as 800 megahertz. This is one of the top level machines available. And the range which is available is 100 to 800 megahertz. These are the machines which are all over the world in various kind of laboratory. They use this kind of ranges for doing the various
So,
experiments. Yeah.
transition of proton means protons go to some other state inside the nucleus.
No, it's a magnetic moment. Zeeman split. It has two levels. There is a transition frequency for going from one level to another.
We are not talking about the whole nucleus, proton plus neutron, only proton we are talking about.
Proton is the nucleus of the hydrogen atom. There is nothing else.
So this is the special case.
Hydrogen atom. So they use as the standard. It's one of the most common element available to specify various things. Doesn't have anything other than the proton. You ask what is going to be the frequency for the transition between its two levels, and you come up with a number, and these are the numbers basically quoted. Okay. You can give more detailed numbers if you want, but these are, well, I can write down some number, it doesn't matter. And this magnetic field, this field goes up to 20 Tesla. How far you can go in terms of current technology, and this is as 800 is kind of high level stuff. This is again high level stuff corresponding to that, how strong a magnetic field you can make. It goes up to about 20 Tesla. Of course, you can have it smaller magnetic field, etc., and that will generate smaller frequencies. And to go up to this high field, you need a superconducting magnet, otherwise things don't work, because the power consumption will become enormous if you want to produce this kind of field with just an ordinary electromagnet. But once you make a superconducting magnet, it will be put into that particular configuration, and as long as you maintain the temperature, it will remain there, no resistance, no consumption of electricity needed after the initialization. And well, there is a well-known example in our NMR lab, which I can mention, that they had bought one of those 100 megahertz machines, maybe some 30 years back or something like that, and it ran for many years, did all its useful work, etc. And then they decided, okay, it's enough now, the machine is old, it has served the lab and all this work for 20, 25 years, we should retire it. So they basically, what you call, quenched it. Quenched it means removed this particular magnetic field after 20 years. And when they see it, the currents in that magnet, superconducting magnet, was still running after 20 years at the same strength. And they said now it's the old machine, will retire, basically it means that you will remove it from the superconducting phase. But as long as it was in superconducting phase, it was running without any problem for 20 years. So that is a kind of stability you can get in this kind of systems. And that is actually the power behind using this technology, which is very well developed in terms of all specifications, and just then reinterpret what you can do with that as quantum information processing. Incidentally, I can also say that the use of this NMR was originally for specific structural problems in chemistry and biology. And what they offered in that still continues. You can get very good structural information of all kind of molecules using these NMR machines, and that remains its dominant use. Either it can be in research labs, in academic institutes, or it can be in the medical field as well. And how does that occur? That comes from the next operation in the list. How do the two qubit interactions arise? So the eigenstates of this superconducting physics are 0 and 1, which are on the Bloch sphere north and south pole. Okay. The RF field, if you apply in the transverse plane, it can take the 0 to 1 and back. Okay. That corresponds to the transition. A rotation about, say, x-axis of the spin can take the 0 state to 1 state and vice versa. So that is the way it can perform the transitions. These are called Rabi oscillations in the language of spin half systems. And there is an associated frequency with it. There is an associated frequency with these transitions. And that is what these numbers specify. Yeah, it's a cyclic process. It can go on as you can instead of without any decay or anything like that present. You can choose your axis whatever you want. That is not a problem. But you need two orthogonal, two non-collinear axes to be able to perform any operation on the Bloch sphere. Well, you just have to go back to the equations for dynamics. This RF field is actually applied as pulses of specific durations. So you're rotating about this axis, but the pulse duration will tell you what is the angle, how far you go, and you can stop. If you want to cycle it for a long pulse, it can generate this kind of transitions and process, but you can apply the fixed duration pulses. So yeah, that I should write down. Yeah, rotation angle is specified by the duration of the pulse. It's just integral of the Hamiltonian with respect to time. The time range is limited, it will rotate for some angle.
The transition frequency, is it invariant with the frequency of the RF field?
It's connected to both because the splitting of the two levels is decided by this background DC field. Okay, and the transition frequency is basically that splitting divided by the Planck's constant, delta E divided by H. So it's linked to that as well. But the transitions are implemented by the RF field. And it has and this is just a fundamental number given some delta E specified by some field strength, what is the frequency for it, and all that thing is connected with the third letter which is sitting inside here, which I have not mentioned, resonance. It's going to come back and apply to this particular process about how various things are put together. Right now, I'm not saying anything about the resonance. I'm just saying the spin and a magnetic field, this is what it will do. But we have to use the resonance feature to be much more specific. Okay. So now there are two qubit interactions. Where are they going to come from? And there is only one way. There are individual nuclear spins and they need to interact with each other. It's one dipole at one location, another dipole at another location, and they can have some effect with each other. And this is the interaction, but now it depends on the distance between the two nuclei. And that distance is decided by the three-dimensional shape of the molecule. What will interact with what? And well, one has to know the geometry in some sense to be able to deal with that. But that is a part which is connected with various operations. And the way this influences various processes are detectable in actual experiment. And the important I can just leave out the resonance, just call it transition. So to explain this, let me go back to this example of hydrogen where I said that in a good machine you can get a transition frequency of the order of 800 megahertz. But this will be the transition frequency of a free proton. What you have in a real molecule is a proton with other components and other atoms nearby. And those nearby atoms do interact with the proton and they produce certain chemical shift of the transition frequencies. So once you have a free proton, it has specific frequency, you put it in a molecule and then measure the frequency, it will be slightly shifted. And the shift depends on who are the neighbors and in what arrangement. And that is why it is called chemical shift. And this can be measured. That yes, proton when it is free, it has a certain frequency. You now put it in some organic molecule like chloroform and measure its frequency, it will be slightly shifted. And the way the most dominant use of the NMR is carried out is through observations of these chemical shifts. So we are going to use it in a different sense, but this is where the major use of the NMR technology is, that measure you can figure out who are the neighbors by observing the magnitude of this chemical shift, and that is something which can tell you about the structure of the molecule. This is how chemists and biologists use the NMR machinery. They deduce the structure of the molecules by measuring the NMR spectrum. It's a complementary technique to what crystallographers do. They take a crystal and they do X-ray diffraction and figure out what is the structure or the arrangement of various atoms inside that material is. But to be able to do that, you need to have a regular crystal which can give a result with X-ray diffraction. Here, you don't have a crystal. You just have a single molecule. And this technique allows you to determine the structure of a single molecule. And so it's used in a complementary sense. When you crystallize, you use one kind of technique. When you have single molecules, you use some other kind of technique, and then you learn about the structures of atoms, and particularly this machine, NMR machine, gives you resolution which is at the level of a fraction of an angstrom. by giving you the values of the chemical shifts. So it tells you that this is the structure of the molecule in 3 dimensions. And this is how the chemists and biologists use the machine most of the time. The information processing, we are going to use it the other way. We assume that we have designed the molecules and we know all the chemical shifts available for it. Now we want to do certain operations on it, and we will use the knowledge of these specific frequencies to perform these resonant operations. That is what is important. Okay.
So,
Yeah.
these chemical shifts depend only on the distance between molecules or their orientation also?
Hmm?
These chemical shifts depends on distance between molecules or
Not molecule, distance between nuclei.
inside one molecule?
Nuclei are inside the molecule, but they define the position of the atoms.
This is for one molecule, right?
So everything is just one molecule.
It is little dipoles interact with each other. It means dipoles inside one molecule.
Dipoles are the nuclei with spins. They are going to interact.
There it is written two qubit interactions. So I thought there are two molecules.
Hmm?
It is written two qubit interactions. So I thought there should be two molecules.
Yeah, so far I am talking about only one molecule. We'll go to how do you actually observe this thing, which is a different story. I have to give some more reason for doing that, or other numbers are needed. And incidentally, these chemical shifts are what is known as measured in scale, which is parts per million. And they are of the experimentally found, they are all in the few ppm range. That means you have certain frequencies over here. These things are going to be 1,000,000 times smaller in the frequency. So all that's another label which is used, that all labels are given in frequency space. It's a convenience. In physics, you are more comfortable dealing with Hamiltonian, which has a unit of energy, and frequencies can be obtained by just dividing out by the Planck's constant. That is nothing complicated, but the literature, if you look, everything will be given in terms of frequency. They will not talk about energies explicitly, but everything is just interconvertible, and it's basically choice of labels. Okay. So now let me come to a description of this setup, which I can describe, or rather it's little more complicated. Let me tell that part of the story as well. That they occur at this radio frequency range, which are of this level for 1 qubit process, single qubit process, and chemical shift, if you want to observe, it will be million times smaller, which will be just 100 to 800 hertz. Forget the mega part of it. And these are all in the electromagnetic spectrum in the radio frequency range. So the question is, can you detect it with any instrument? The answer is no. Too small in terms of any observable signal. So what is done is not a single molecule computation. If it was observable, you could have directly done it in that particular manner, but it's not observable. So the way it is made observable is you take lots of these molecules and perform the same operation on all of them, then it will produce a signal which will be kind of magnified, it will show up in your detector. And that is a label which is called ensemble computation. It performs same operation in many identical molecules, and how do you make sure that they remain sort of independent of each other, and that is you put them in an environment that they are sufficiently separated from each other, which is a dilute solution. So the way this technique works, you take that particular compound, dissolve it in some solvent, which is dilute in terms of its concentration. So there are many molecules, but they are sufficiently far away from each other, and then you perform the same operation on that whole ensemble, and it will produce a signal which you will be able to detect. And well, you have to give some number. How dilute solution is typically concentration is something which is called millimolar, which is 1 part in 1,000. Okay, so just to give some numbers, a mole will correspond to an Avogadro number of molecules, 10 raised to 23, something like that. So millimolar means that you will take 1000 of this, about 10 raised to 20 molecules and dissolve it in 1 mole of some solvent. And then it is dilute enough so that these things are able to perform their job independently, and you take the collective statistical signal from all these simultaneous events, and that will give you something which you can detect. And of course, you have to, well, kind of make a choice, because if you make it too highly concentrated, then the molecules will start interacting with each other directly, and they will not give you identical signal. If you make it too dilute, then the signal will go down. And this is roughly the range where things work, and that is where people use this particular strategy. So this is a important part of the story. But now it has to give various physical specification that you are going to not deal with it atomic level. You will have a solution of some particular concentration, and it will occupy a certain volume, and then you have to make sure that all this machinery works on that particular volume in a what you call fixed accuracy. Okay. So these are fields which you are generating, they must be uniform, because the molecules are not going to be spread over a certain region. And this volume typically is of the order of little centimeter cube. And the remarkable fact is that these magnetic fields are made accurate up to 1 part in 10 raised to 9. This is high technology, that you have to design all those things completely uniform, but it is possible. And then everything which is there in that particular volume will respond the same way. So that now gives a setup which is something you can find in all the NMR textbooks, that you take some sample which is a solution, and put it in a test tube. It's just some small thing of this particular size. Then you put this superconducting magnet. So and the notation is used for this one is called B0. It's a static field. It's produced by certain coils, Helmholtz coil to be precise for getting this high level of uniformity, and it is something which remains fixed. You don't touch it at all. Once you kind of made it into that initialization machine, and it has to remain at liquid helium temperature to be in the superconducting phase. And then you apply, this field is in this direction, and then there is another coil which is orthogonal to this direction, and this is the radio frequency coil, and it produces some field B1. And this is the one which you can apply it in pulses for specific durations, whatever you choose. This one remains permanent. It is there forever. And in this setup, all the experiments are done. Of course, there are many things which you need to do with high accuracy, and so you don't do it yourself by dialing some knobs. It's all done by, you program a classical computer to control all the knobs which are there in this particular machine. So there is a classical computer which controls this NMR processor, which can do some quantum job. So this is all controlled by So now let me come to the question of resonance. And it is needed to address a specific nuclear spin. Why so? Well, this is the setting, but I want to perform some transformation on one particular nucleus on this molecular register, and don't do anything on everybody else. How do I do it? Well, again, the limitations of electromagnetism are all well known. You wanted to study a crystal, you needed an X-ray. Why X-ray? Because the wavelength of the X-ray was comparable to the separation between the atoms, and that's where you could see whatever was there in the structure. What is the wavelength um, of the radio frequency range? And the numbers are there, no big deal, convert frequency to wavelength. The radio frequency, these numbers produce some wavelength is like 1 meter. There is no way you are going to focus at 1 meter wavelength onto one particular atom, way apart. So that is where the resonance comes in, that you shine that particular RF field, it is going to touch everybody, all the atoms, all the nuclei which are in the sample. But you choose its frequency so that it is in exact resonance with some transition, and all the other transitions will be somewhere away. Okay. And now it is a phenomena which is well understood, that if you have a, say, a two-level system and you have some natural frequency of it, if the frequency matches with it, you will create a resonance. If you are away from it, it will just create some random noise and it will not grow in amplitude. So only where the particular frequencies which matches with whatever you are shining, then you will have a large amplitude. And for that, the nuclear spin frequencies have to be well isolated from each other, that when you show some RF field to it, only the ones with match with it will go into a large amplitude, the other ones will remain more or less quiet.
When we are like putting the static field, we are putting constant static field across it. And shouldn't the universality of the molecules ensure that the transition is like the splitting is common for and same for all the molecules?
Yeah.
Then how can we like isolate?
That is because of the chemical shifts. The frequencies are shifted a little bit because of the local interactions, and you have to design a molecule so that all these chemical shifts are sufficiently well separated, and then you can address them one by the resonance phenomena. And this is it's like in any oscillator. You have a natural frequency, and if you driving field will match with the frequency, it can increase in amplitude. Just have to make sure that any nearby frequency is there. This field will not cause much perturbation. And it basically comes down that different frequencies have to be cleanly separated from each other. If you can do that, then the system will work. So that is what is done in practice. And yeah, I should have mentioned some other properties which are also used in maintaining these solvents. They also have to be this what you call you are putting the molecules in some solvents, but you have to make sure that that solvent does not bring any of its own signal into this business. So those have to be non-polar. For example, water won't do. It has a huge dipole moment. It cannot be used as a solvent, and typically what is used are organic solvents. And which don't bring in their own magnetic dipole dynamics into the picture. They have to remain completely outside of whatever else is going on. And one of the popular compound is what is called a deuterated chloroform. Okay. Chloroform is a CHCl3, and that if the H is there, it creates a nuisance because it's all over the place in the dipole. We don't want that the hydrogen is substituted by a deuterium, and then this is a non-polar molecule which does a job of providing a background solvent which will not disturb the dynamics of the molecule which you are addressing with all the nuclear magnetic resonance. So there are all these bits and pieces of machinery which people have pushed together over the years, and it has worked basically fantastically well. And the last thing I can add is just let me give the limitations. So this is all kind of background material. In the next lecture, I will give an explicit description about what is the Hamiltonian, what are the operators, how do you generate transformation, etc. But before that, there are all stuff which is needed and which has gone in. And limitation comes from all this description quite naturally. And one is that the size of the molecule limits the size of quantum register. How many qubits want to put? Well, you are putting some 10, 15 atoms, maybe you can do that. Can you make a compound which will have 1,000 atoms? Well, that's a tough job. It doesn't work arbitrarily well, and I will give you the numbers that how much people were able to do with this particular setting is some order 10 atoms they could handle. This is the size of the molecule. Can't go very far beyond that.
Beyond that, quantum effects will go. That's what
No, all the problems of addressing various components become terribly complicated. you need all this criteria. You put too many things together, you need the resonance, you need isolated frequencies. All those things are get crowded enough, and then you can't do a good job. The second problem is much more explicit, that this statistical ensemble distribution which is what we describe generically by the partition function, that the probability is proportional to e raised to minus beta h, and the z is the normalizing constant. Beta is the temperature and h is the Hamiltonian. Now, what we know in this particular case, what is the size of the Hamiltonian? Well, it's given. This frequency completely tell you how much is the splitting between various energy levels. Maximum is some 800 megahertz. So you put in some numbers. Of course, this is frequency, and you get to energy, you have to multiply by Planck's constant. That's fine. This is understood. The 1 over beta is the temperature, and you can evaluate this number at room temperature. It's about 1 over 40 of an electron volt. And then you now calculate what is beta times h. And it turns out to be ten raised to minus 4. Okay, so then I can now, number is so small, we'll just a Taylor expansion. So it's identity minus second order terms is too small, we'll just ignore it. But what is the normalization in front? Well, it's a replacement for z. It's completely decided by the condition that trace of rho equal to 1. So this becomes one over 2 to the power n. And this is the drastic constraint. The signal is all in here, in the Hamiltonian. If you have an identity density matrix, you do whatever unitary stuff, nothing happens to it. And that is dying with the increasing of number of qubits, and it is dying exponentially. And that is the reason where you are getting stuck at some number of atoms. You go far, the signal is so small you can't see it. Yeah. Hamiltonian is? Yeah, it is roughly just the scale. The total Hamiltonian will have both the background field and this, both B0 and B1, etc. But roughly the scale is given by this static field, which is the largest term in the Hamiltonian. It will have multiple parts, that is a different story. So, the signal decreases exponentially with the size of the system. And that makes it very explicit that, well, how far NMR techniques went, they went up to about 10 atoms. 2 raised to 10 will be like 1 over 1000. It's already down and you can't go too much below that. Okay. So these are all the overall ideas about what is there in NMR and how things are going to be put together. And with all this thing, the next lecture I will be able to describe explicit algorithms, which basically means that you apply various operations, part of the Hamiltonian one by one, single qubit, 2 qubit operation, and how it will generate the logic gates that you are interested in. Okay. Yeah, there is one more thing which I kind of forgot to mention, that this RF field is specified by various kind of pulse. You can design the shape of a pulse as some function of time, whatever you want. If you don't want just a square wave kind of situation, it is available. But these chemical shifts or this interaction between these dipoles, they are permanent. These external fields you can turn off and on, but these internal interactions between various nuclei you cannot turn off. So they are always on. And that requires another ingredient, that you have to start the computation at some time and stop at some other precise instant. Because otherwise these permanent interactions are there, they will keep on changing the state. And that feature will come in the design of the algorithm, which I will describe next time. I just want to add one more feature to all this machinery. This is the most popular setting, what is called liquid state NMR, where each molecule acts as a particular information processor, and you do all the manipulation to get the necessary signal. But people have gone beyond that, well, explored something beyond that to see whether you can find more general scenarios. Nothing as successful as the liquid state one, but at least the ideas have been tried, and I will mention a couple of them. I won't say anything more about them after today, because that is still something which is wide open. What can we do by changing some of these features? So yeah, I forgot to give examples about what are the nuclei which are used most of the time. So in this particular case, one of them is a hydrogen, and another one is a carbon-13 isotope. Those are the two which are used most of the time in all the liquid state NMR situation. Sometimes you use other atoms, but these are the most common organic compound ingredients, because this all the biological and chemical applications require dealing with organic molecules, and they do everything using carbon and hydrogen. Sometimes they use phosphorus or nitrogen. You have to choose a particular isotope very carefully so it has a spin half. So both of them have spin equal to half, and the electrons don't contribute anything beyond that. So in the liquid state, there is a particular choice, but one can ask, can you use other nuclei where the spin is not half? They are available. There are many examples, and can you do anything with them? Now you have to be careful, because if you put it in a magnetic field, it will just give us Zeeman splitting, which is uniform. It's proportional to the third component of the spin, and if you have spin 1, you will have 3 levels, but they are all equally spaced. So if you look for a transition, you will not know whether it is this pair or that pair. You have to introduce some kind of nonlinearity in the spectrum to be able to distinguish and that can be done by changing the background. And one of the possibility is that Zeeman splitting, which is just a dipole interaction, you introduce a quadrupole interaction. A quadrupole interaction generates a contribution to the splitting, which is proportional to the square of the magnetic field, and so the spacing will become nonlinear, and you can address one versus the other. And this is something which is available, and it was done by Anil Kumar's group by using the different solvent which was not a liquid but a liquid crystal. And liquid crystals are not isotropic liquids. They can be oriented by applying an external field in a particular manner, and they provide a quadrupolar background. And then you can use spins which have larger values, and then you have to use less number of qubits, larger spaces available in a single nucleus itself. And the experiment which was done by Anil Kumar's group. So they did a particular compound which involved cesium atom, and the property is that it has nuclear spin which is 7/2, and put it in a liquid crystal medium. So there are 8 levels. They all could be individually labeled. And so it is equal to 3 qubits, but sitting inside the same nucleus, so you don't have to worry about what you call this dipole-dipole interaction between qubits, etc. Just one particular nucleus was enough. And then what can you do with these 8 levels equivalent to 3 qubits? Well, they demonstrated 1-bit addition and subtraction. You can calculate A plus B equal to C or A minus B equal to D. Trivial thing in terms of calculation, but great to be able to show that it actually works. Using just a single nucleus. Okay. So that is some direction which is possible. Nobody has tried to build on it in after that. The other thing which is being explored these days is something which is called a solid state NMR. So this again is different from the liquid state in the sense that you don't have the rotational symmetry anymore. So it is like different background field which is built inside. So and this various spin levels, they get split in different manner according to crystal symmetries, and then you can perform certain operations between these levels to do certain kind of transformations. There are groups in many places in the world these days. They are trying various tricks with this solid state NMR. Demonstrations of some simple things have been made, but nothing complicated has come out so far. But that is also possible, and the idea is that all you need is basically a set of well-characterized energy levels with capability to address them individually. And if you can do in various different geometries, it's well and good, but if you have this, then you can apply all the generic machinery which has been developed for NMR. And it's a open problem at that particular stage where you don't have to talk about individual qubits and various operations. You just talk about Hilbert space and various transitions in the Hilbert space. That can give you a description, much more generic description of whatever happens in an algorithm. Okay. So this is an open problem. You can make whatever you want, cast it in this particular language, and that will be something, well, interesting to do. But that has not been done in any large scale. Most of the things were done up to about 10 atoms, and people saw that it's saturated, and that has not progressed much beyond that. Okay. So yeah, next time I will give quantitative description of algorithms.